Please welcome to the stage the CEO and co-founder of Gravis Robotics, Ryan Luke Johns.
Hi, good turnout. Thanks all for coming. So I'm going to talk to you about what we do at Gravis Robotics, which is turn earth-moving machinery into robots, right? So you're all very aware here about the importance of the construction industry, the challenges we have to drive productivity to meet the construction demands of data centers, of renewable and resilient infrastructure. And the way that we're doing that is with this piece of kit we call the Gravis Rack. It's a modular kit. It contains there on the front a LiDAR camera. We've got GPS masts that go on the back that give you surround view camera and LiDAR coverage. We put this kit on a bunch of different size classes and types of machines, and it works both with new electrohydraulic machines and also with conventional hydraulic pilot stage machines. We just retrofit an off-the-shelf valve block onto those machines. And what that gives you is many things. But the key reason that a lot of you are here for that autonomy, right? We can dig, we can drive, we can do trenching, we can do bulk excavation, we can do truck loading, hopper loading, screener loading, fully autonomously. And we've done that across two core machine types, right? So we're really focused here on excavators and loaders. Excavators, we've done machine size classes from 6 to 40 tons. We've done a dozen different brands. We've got a lot of great OEM partners that we work with. You see some of the names down below. We work with 10 different brands directly in collaboration. You see there on the right our first wheel loader. So this is a new product that we're working on. This is something that we introduced together with Case. And this is basically doing all of the terrain scanning using the LiDARs that are on the kit to understand, for example, the traversability of the terrain around it, how it should not drive into things, how it should plan efficient paths to get from point A to point B, how to fill that bucket efficiently. I'm going to spend a little bit of time talking about that. It's one of the most important problems with these two kinds of machines, right? How do you get that dirt inside that bucket? Here, detecting the truck bed using camera and LiDAR and being able to kind of do that whole cycle job from detecting the truck, detecting where to attack the pile, and being able to load that vehicle. One of the reasons that we focus on these two types of machines, there's a couple of reasons. One, important for the financial people behind us is the volume, right? So excavators and loaders, really important machines in the market, right? Together they account for about 90% of the sales volume of these key earth-moving machinery. And if we just look at the bigger than 10-ton excavators, that's 41% of the market. And then together with big wheel loaders, you get about 60%. And if you look at loaders and excavators across all sizes, you get close to 90% in terms of sales volume market share. But the more staggering statistic here is that these machines are being produced by about 1 million a year, and they do about 10,000 hours in their lifetime, right? So if you think about that, we're putting into production 10.5 billion operating hours every year across the globe. Right? So these are hours where if we can make those have a little bit more productivity, a little bit more impact, there's a tremendous potential to increase what we can do in construction across the globe. The other reason we focus on these type of machines is our own background. So we're roboticists. We come out of, a lot of our founders are PhDs coming out of a university called the ETH. And we see that the machines that we work with are a little bit different than some of the other off-road vehicles. If you look at a compactor, you look at a haul truck, you look at a grader or a dozer, a lot more similarities to, let's say, a Roomba or a self-driving car, right? You're driving a path back and forth. You're driving sometimes generally on a pre-marked road, and you're going from point A to point B. You can use GPS to stay in my lane. And it's really important that you don't crash into stuff, right? You don't want to crash into people, but you also don't want to crash into rocks or telephone poles or pretty much anything, right? Excavators, on the other hand, are a little bit different because they intentionally crash into stuff all the time, right? It's a very different problem than a vehicle, right? You're not only needing to interact and move that environment, you need to know kind of what's what. And you also need to be able to do that efficiently, to feel that complexity of the soil. And you're also changing the world as you navigate through it, right? A lot of the self-driving cars, they'll go out, they'll pre-map the entire world, right? They'll pre-map where the roads are. You know where that building's supposed to be. Here, we're actually changing that world as we move through it. And one of the other challenges of that world is that it's more than what you can see, right? There's complexity in the ground. You have frozen soil, you have rocky soil, you have sandy soil, you have clay. You've got all of this different variation that can happen just in one single scoop of that bucket. And so we see this as much more of a robotic problem, right? It's a manipulation problem. If you think about the space of robotics, you've got a lot of things around locomotion, you've got a lot of things around manipulation. What do those hands do? And if you've been following the kind of robotics market, a lot of work in humanoids, you see them dancing, you see them doing cool stuff, but getting that hand to do stuff is still a really big challenge. It's heavily unsolved. Our background in robotics is, I would say, pretty amazing, coming from originally the space of quadrupeds. So getting four-legged robots to navigate and manipulate and do things in the wild. So our founding team is actually the winner of the DARPA Subterranean Challenge, kind of like the biggest grand challenge in robotics, getting robots to go and explore caves in the most complex, unexplored environments where you're totally GPS denied and you need to go around, find obstacles and do things. We won the $2 million prize there, beating out teams from the most eminent universities across America. And if you look at how we got started with excavators, it's an interesting story. So we're from a university in Switzerland. As you might tell by my accent, I am not from Switzerland. But we basically are from an area where nearby there's this excavator, this spider excavator. How many of you, raise your hand if you guys know what a Menzimuk is? Okay, a couple of you. So this machine is a super complex excavator. It's got 23 axes. It's got its wheels on its outriggers. It's got a telescoping stick. And it's an awesome machine, right? It's made to be able to climb crazy alpine environments, be able to navigate all kinds of complex terrain. But if you look really closely, right, we've started with a quadruped. It's got these 4 legs. And if you look at this version of the quadruped, which we've got now being able to step and drive around, and this arm, not so different from that hydraulic machine, right? So when we started looking at that, we thought, well, we can make this 4-legged dog walk around. Why can't we make that big hydraulic dog walk around? And so that was the first thing we did. So our CTO, Dominic, he started working on the hydraulics of that system and got it to be able to navigate, self-balance across incredibly complex terrain. And that kind of got us on the road to being able to start doing tasks with that machine. How can we use hydraulic machines to do more and more complex behaviors? My own PhD was focused on getting that spider excavator to completely autonomously build stone structures. So we would get this machine, we'd put it out into the world, and it would find stones. We could give it bits of debris, we'd give it chunks of granite, and it would go find those rocks from the environment, pick them up, actually use that rototilt to 3D scan that stone in its hand to build a 3D mesh of it. It would then put that mesh down on the ground and remember where it went. And then it would go and plan what is not only a kind of geometric structure that I could build, but one that actually is stable, that kind of follows the rules of the structure, and that constantly adapts. So you see here this LiDAR scan that the machine is making. As it's building, it's re-scanning that wall that it's building. And it's understanding how every rock settles. And then when it goes to place the next one, it's doing what a human does. It's thinking about the stability of that structure. It's thinking about what might happen if it places that next rock here, and it's replanning, right? So this is a world where you can't pre-plan this entire wall. Imagine that you would set up some amazing algorithm, plan this whole wall, and then what happened all the time, some guy ran off with a rock, or a rock broke in half, right? You've got to have that adaptability to be able to change based on what's happening in the world. So this is one of the walls that we built toward the end of my PhD. It's part of a park that's near the airport in Zurich, and there's a section that's autonomously landscape. That's me with the hard hat there. And what's really cool about this structure is that because the robot 3D scanned everything, we've got a perfect digital twin, right? So we know where every stone is, we've got a mesh of every one of those objects, and we can really understand things like the void ratio, the way that that structure was put together. And what's more is that because those materials they're not worried about like the skill of an operator, right? Sometimes building stone walls is becoming a lost art. I've met some people on the tram here who still do this work. It's a really, really hard job to do well. I would say right now, autonomously, we're not nearly as good as some good operators at building a really nice structure, right? But when we looked at the carbon emissions of building this structure, about a 78% less energy going into building that wall than building the exact same, much thinner, structurally performing concrete wall. Right? So just because we're able to use these complex materials without having to industrially process them, because you've got a robot that can understand and adapt to that environment, we're able to really, really increase the kind of sustainability of the structures that we build. So we see that, robotic machines can change for the better the way that we build projects from a design perspective. Really cool outcome of this for me is that this project is also featured in last year's Guinness World Records. So it's a very arbitrary record. I would have never imagined as a kid, largest stone wall built by a robot. But pick up a copy. It's pretty cool. We're pretty proud of that. But now as a company, we've kind of spun out from the university and we're focused on solving the most ubiquitous tasks, those challenges that you see every single day. More than 70% of what these machines do, dig, right? And you might ask yourself, like, well, why do we need so complicated robotics people to be able to solve these problems, right? It's just like you just scoop some dirt, right? But it's a really, really hard problem. So one of the things that's different about like an industrial robot arm or a quadruped robot that's running with electromagnetic motors is that these machines are really hard to model. They're really hard to understand. And some of the reasons for that is because you've got multi-stage hydraulics, right? So there's a little bit of delays and dead zones that happen in that system that are really different depending on how that valve was manufactured. And there's a lot of complexity between manufacturers or even between, one machine one day and one machine another day. You've also got a lot of variation in the tolerance of that system being manufactured, right? So limb lengths are different, the kinematic assembly of that machine is different. You don't get this kind of understanding from the factory of, sub-millimeter precision of where all of those cylinders are. There's a lot of kind of slop in that overall system. You've got coupling effects from having one big motor, right? So if you are kind of fixed in the amount of hydraulic fluid you can push through, you get a different behavior when you move your stick by itself versus when you move your stick and your boom and your cabin turn at the same time. And all of those affect the way that braking happens, the dynamics of the machines happen. And this is a variation that happens not only between machines, right? Not only between brands and size classes, but between two of the exact same machines. You've got temperature changes that affect the way these machines work. You've got changes in friction, the way that those cylinders are moving. At the same time, you've got a huge amount of variation in the world itself, right? So you've got full buckets, you've got empty buckets, you've got hard ground, you've got rocky ground, and you have to kind of stay within the torque limits of that machine as you're operating it. And the way that we solve this, I think there's a lot of different approaches to solving these kinds of control problems. For us, we see that you need a lot of data, right? We need to get data from machines. We need to get data from kind of operations to understand that variability, be able to get a generalized intelligence that lets us understand those unique behaviors and be able to actually leverage them, right? If you understand those coupling effects, you can drive that machine even faster, right? An operator who's driven that machine for 20 years, right? They understand when to let go of that stick because they know just when that machine's going to start slowing down, and that changes depending on what's going on with the bucket. So really hard, you've probably, if you've been looking at the world of humanoids, you've found that very hard in today's environment to get enough real-world data, right? The LLMs that we're used to now, everyone's using ChatGPT. This is coming from 30 years of data, of everyone putting really high-quality data onto the internet. And it's coming from centuries of book data, of very clean knowledge about how to write a good English sentence, right? In the physical world, that data doesn't exist yet. We don't yet have a public internet that gives us a database of how soil interacts, right? Of how objects fall over and move. But what we can do is we can create, and this is where a lot of our expertise has been, is in building a very, very efficient simulation model that lets us actually run thousands of machines in parallel to train much faster than real time what these behaviors are doing, right? So we can learn in sim a lot of these kinds of coupling effects and build what's known as a world model that defines not only that soil, but also those hydraulic behaviors. So as a company, we've done more than 1 billion cubic yards in simulation, tens of billions of cubic yards, right? This is like thousands of operators' lifetimes of experience in training these models. Very, very difficult to get that level of control if you're only looking at real data, right? So it's one thing to just, this isn't the same as saying, look at one machine and try to understand what it's doing by imitating an operator after a month or two of kind of watching what they do, understanding when they let go of the skip. We want to get better than those operators, right? We want to get to where this machine is operating at the fundamental limits of those hydraulics so that we can actually get the OEMs who are in the room to make a better machine, right? We want to be the driving force to make productivity at the maximum capacity of what that machine can do. And so our system gets better and better and better over time. What that enables practically, right, is a very simple thing. But for an operator, this is really easy. For a robot, this is really hard. It's where a lot of companies have struggled to be able to dig effectively in different kinds of grounds. So you see here, 2 different shots, 2 different machines. They know nothing about what's the ground made of, right? The ground doesn't look different. Well, on the top left, it's a little bit darker, right? You can guess that that's a bit softer. But here on the bottom, no visual difference between those grounds, right? So what you used to do when you're trying to do autonomy with an excavator is you would treat it a bit like a tool path from a CNC machine. You'd say, well, go down like that and then take this kind of parabolic scoop. But when you try to follow through that motion and you hit a stone under the ground, what happens, right? You keep pushing and then your tracks start tipping up, right? The revs start going up. And all of a sudden, that machine keeps falling through, and eventually it breaks free, slams down on the ground. You come up with a teaspoon of dirt in your bucket, you turn and dump it, and now you've taken about 100 times the amount of time to move that volume of earth as if you had had a full bucket, right? And it's also horrible for the machine. But what's happening here is the machine has learned to look at the pressures in the hydraulic system. It's learned to look at the behaviors of those interactions, and it gets a reward when it gets a fuller bucket, right? So it's actually being heavily optimized to say, let's get a fuller and fuller and fuller bucket as it digs across those many, many, many cycles in sim, but also in reality, right? So you see here where the soil is soft, deep scoop, heaped bucket, right? That's exactly what you want to see. They're heavily compacted soil, right? Ground very, very hard, hasn't ever been dug in, a century. But what you're seeing here is that machine using those teeth, breaking into the ground. You see it kind of pull up when it's hitting too much resistance, and it dives down again. It's still kind of being able to fill that bucket very effectively. And then a most extreme case here, it didn't know that there's a boulder here under the ground, right? But as soon as it hits it, it's reacting to that. And then as soon as that boulder ends, it's kind of diving in again and coming up with the full bucket. And that's something that even good operators have a hard time being able to react so quickly to, right? We're able to tap into the very, very low-level hydraulic signals. We don't have to wait to feel that delay of, the bucket's not quite moving. I'm feeling a little bit of, increase in RPMs here. We're able to kind of do that very, very real time in the way that we control this machine. And the value there, of course, if you think about that relatively fixed hydraulic flow of the system, your turn and dump cycles, if you're a robot, very, very consistent. So the one thing that's driving productivity, that's driving kind of dollar savings for our customers is just how full is that bucket? What's the average fill rate of that bucket? What's the cycle time? And how consistently can we do that? And we've deployed this system across a variety of projects, so looking at things like screener loading, trenching, truck loading. And in some of these tasks, we benchmarked a pretty good, like across 20 days or a month of comparison between human operators and our system. We're seeing in some cases 30% increase in productivity. It's very different depending on the soil and the task, but in general, our goal here is to really drive what these machines can do. I'm a firm believer that the value of autonomy is not removing labor, right? We need every bit of labor we can get on jobs. It's about making that labor do more, driving one machine 30% faster, driving 2 machines 30% faster, driving 10 machines 30% faster. And we've been able to show that not just on one type of machine, not just one brand of machine, one type of truck, right? But we've got more than any autonomy player out there, the biggest variety of machines, right? More than a dozen different brands, more than 10 different types of size classes and machines across 7 different countries right now we've got deployments. And this is giving us that awareness, not just of how to control, again, one type of machine, but how to approach that vast variety of tasks to be able to build up that data that lets us build better and better and better models over time. Talk through here a couple of those examples of the kind of work that we've done. So one project that I'm pretty excited to announce here at CONEXPO is a collaboration we have with a South American contractor, Tekin, who has 2 36-ton Cat machines working on a project doing 60 miles of oil and gas pipeline in Argentina. And this is like, you know, we tested a lot of our things in simulation. We test a lot of things in a test site. But this, you see here the rocks coming out of this ground, right? This is incredibly dense, super heterogeneous ground, right? You're digging through, you're breaking through teeth on the bucket very consistently. You've got bedrock sometimes that's less than 2 feet below the surface. And we've got to have a machine that can actually adapt to that and be able to dig day in and day out through these kind of very, very difficult and challenging conditions, right? While at the same time also being really careful to not, you know, hit things like the adjacent pipeline that's been laid out. And so on those kinds of projects, we see that productivity, right? Like there we're measuring close to 30% in the preliminary data that we have. Productivity is a key metric, right? We can dig more. I talk a lot about that. How can we dig more? How can we get these machines doing more? But here's another example. This is a site where we're loading a screener. This is a Wholesome quarry site in the UK. And there they set a production target, and we exceeded that production target by 33%. We're actually limited by the capacity of the screener. And what's important in these kinds of jobs, right? So if you're using these machines in production environments, you don't always have the luxury of saying, let's just do 30% more, right? You've got a limitation from those belts, you've got a limitations from demand, you've got a limitation from the other machines that are on site. But what you can do, and was really exciting for Wholesome, is working together with us in Devlon, they can actually go down a size class or 2 a machine. So every 15% that you're increasing production capacity, you can go down a size class. And if you can go down 2 size classes, give you a lot more buying power, gives you a lot more ease of transport, of maintenance, of service, and you know, it's just overall a win for everyone. What we've seen, though, in bringing this system out into the world is that it's not just about having great hardware, it's not about having great AI, it's really about how you bring technology to the operators who are doing this work, right? The ones who have the real knowledge, the experience on site, because if they can't use it, right, it doesn't matter, right? And what we want to be is a tool, right? We want to be a tool that operators can very flexibly use and they can immediately understand and interpret. And so we do that by connecting a tablet we call Slate, you see on the screen here, to this system we call the rack. And it gives you a number of things. So one of the things that it gives you is a number of views of what's going on around the machine. So the first one there is a real-time 3D survey. So if some of you have used, you know, drone scans, things like Propeller Arrow, this is happening in real time on board the machine. So it is using those LiDARs that are on our kit to take a 3D scan every single second, right? So you're understanding what terrain is moved, whether you're moving it, whether a machine next to you is moving it, you're measuring that environment and you're mapping what's going on. And what's more, we're able to import 3D models. We're able to set, you know, target terrains really simply on that device. And we're coloring that map based on the cut fill that's needed. So if you're sitting in the cab or you're outside looking at the system, you see anywhere that's blue, I've got to dig. Anywhere that's green, I'm on grade. Anywhere that's yellow or red, I've got to fill. So even with a machine guidance system today, what you see is a little rectangle of a bucket and a line of where you need to go, but there's no understanding what's the real world, right? Where's the real ground? So you got to fish around, you got to get a benchman going around checking grades. Here you see instantly in that 3D model view, what's high, what's low, what do you need to do to get that job done? The other thing we do, and you know, some of you who have used a guidance system would recognize, you know, you got the bucket here, you got that target grade. But we also give you that section cut, right? So you see here in black, this is a cut at that bucket plane of that real Earth situation, right? So you see immediately, hey, I've got to push this material out, I've got to cut that material back. Makes it very, very simple to do work, also manually inside the machine. And that's a system that a lot of expert operators really prefer, right? We've had operators who have driven machines for 30, 40 years, and they say, you know what, I don't look out the window anymore, right? I'm just looking at the screen because it gives me such easy perception of what I need to do. But we also offer this in this augmented reality view. So we take that 3D map, and because we've got a really good calibration on that camera, we can overlay it over that camera feed to be able to show really simple on a video where you need to dig. And for those of you who have tried to get a new operator, a young guy learning how to use a machine control system, right? You've got this kind of like crazy, almost like, jet fighter heads-up display. Can be really confusing. Sometimes weeks of training goes into this. We get people who've never driven a machine, who've never used machine guidance, and they just see immediately, okay, I gotta go dig there, right? It's very, very clear, very intuitive. And what's best is you can just select an area, press play, and the machine will go and dig that autonomously. A few of the other benefits of having that sensor suite on the machine is that we can use that augmented reality, we can use that perception that helps the robot dig safely, that helps the robot know what to do, to also help manual operators know what to do, right? So here you see our people detection system. It's showing you in that augmented reality view where there are people. It's showing you in that kind of top view around the machine where there are people detected around the machine. And it's also kind of highlighting around the screen exactly which side of the machine you've got people on. The other thing that we can use that augmented reality for that we've done on this is a parking lot project near Manchester Airport in the UK with Taylor Woodrow, is if you've got mapped utilities, you can actually import those georeference models and show them in this augmented reality view, right? So if you're an operator and you want to avoid hitting a mapped utility, very easy here to just see that's where that is, right? I need to dig carefully in this area. So it gives you a kind of X-ray view. And if you've got a GPR system, you're doing pre-maps, you can go on, you can load that maps in here, and that'll give you the ability to kind of understand that geometry. And we see the value of this AR not just in helping operators avoid things, but also to do the work that we don't currently do autonomously, right? So we dig autonomously, but there are a lot of other things you do with an excavator. It's a Swiss Army knife. And so you might dig a hole, but then you need to put in some precast manhole riser. You can import the 3D model of where that needs to go and use that augmented reality to actually guide where you need to put that. So you don't need that guy in the hole putting this thing perfectly into place using that GNSS rod because that operator's got that visibility, right? You want to put a bunch of Jersey barriers up in a very special place. Here you've got that visibility. Just do that quickly, instantly, right? So when we talk about productivity increase, it's not just that fast cycle time through autonomy, it's giving that awareness of what's going on around you, right? The ability to just say, we got to go and put this thing here, and you're not thinking twice about checking those measurements. The other really cool thing that I'm proud of about Slate is that it's portable. So you can use this, as I've been talking about, inside the cab. Think about this like, co-pilot. It can guide manual operation. We have a tier that just supports manual operation. And if you have that autonomy subscription, just select an area, press play. Think about it like cruise control for your car, right? So we've got a lot of customers who are interested in leaping immediately to autonomy, but you've also got 70% of the market who doesn't yet use machine control. And so to get those people to jump to autonomy, it's a harder effort. You got to learn how to use those systems. You got to learn how to get into that ecosystem, how to create those CAD models. And here we're able to create one simple gateway that lets you adopt autonomy at your own pace, right? So you can use this just to guide your operators, just to give you that real-time measurement inside the machine. Once you start using autonomy and you found the jobs that autonomy works repetitively in, just take that tablet out, tap where you want it to dig, and it's going to go and dig that autonomously, right? So you've got here, you can monitor that thing, you can see that cut fill, understand the progress of the jobs going on. You see that machine digging in the background, no one inside. And we see this over time, enabling an operator to drive, again, to monitor 1, 2, 3, 4, 5 machines. And as you do that, you're going to get edge conditions. You're going to get challenging situations where you need to step in and take over control. And you'll see we've got joysticks and pedals to just plug into USB to that same tablet, right? You don't need some complex big computer. You don't need some complex stand. This is just joysticks and pedals, plug in over USB, gives you an external monitor, and you've got with this same system also an augmented remote control system where you don't just have that challenge of lost depth perception from one camera because you've got that augmented reality, you've got that 3D view. And so in general, in practice, this looks a bit like this. You've got this tablet we call Slate. It's got this wireless stop on it, so you can always stop that machine at any moment, deactivating the hydraulics. We detect this truck using camera and LiDAR. And then if you set up that task in the cab, you set it out outside, it doesn't matter, right? So you take that thing out, you can dock it into this remote stand, and you've got exactly the same experience that you had inside the cab, right? So we want to enable that fluidity of use that lets people use this in their own way. And I want to spend a minute talking about how we see this kind of technology emerging in the field, right? So if you look at this graph here, we like to draw it as kind of two axes. So some of you have heard with self-driving cars concept like the level of autonomy, how autonomous is it? But we also like to think about where's the operator, how far away? So you got this axis here, level of autonomy. Up there you got location. Are you in the cab? Are you on site in a container? Are you 100 miles away? Are you in the Philippines, right? And what we see is that the way that you adopt autonomy can be very different. There are some players who want to say, let's get operators used to being outside the machine. And then once they're used to outside the machine, we'll gradually add autonomy to those experiences to get them used to that experience. My hypothesis here is that the most important thing in the industry is productivity, right? And when you get a person out of the machine first, teleoperation always has a little dip in productivity, right? You got higher latency, you got the challenges of having a stable network, and you're always not going to have exactly the same experience that you have when you're in the cab. But everyone wants to get up there, right? You want to get to the upper right-hand corner where you got one person really far away driving a handful of machines. And so the way that we get there, the way we think about getting there, the cool thing with our system, as I just said, like it covers all of this, right? You can use that tablet inside, you can use it far away, you can use it manually, you can use it autonomously. So with that one architecture, it's kind of up to you to make your own way to get to that upper right-hand corner. But what we see is that there are a couple factors on the job site that determine how you get there. So one of those is the mean time between interventions. So this is if you've got an autonomous system and you have to take over manual control every 30 seconds, not super autonomous, right? It's not going to be able to do that job. But if you put it in the right task and it's doing that work for 8 hours, right? You've got very, very rare interventions happening here, much more able to kind of step out the machine, but that's also going to drive your productivity, right? Because you've got a lot of consistent throughput from that robotic system. Think about this like a factory. You're able to just dig and dump without any interruption. This is the lack of interruptions, the lack of smoke breaks, the lack of lunch breaks, right? These are the places where the autonomous system really thrives. On the other axis, we see this concept mean time to resolution, right? If you need to come over and take manual control, how much time are you doing to take that manual control? Are you stepping in for 15 seconds to press a button and say, go ahead? Or are you stepping in for 8 hours, right? And the idea is if you're going to step in for 8 hours, you should not be on the other side of the planet, right? You should just be in that cab because you're going to get the most productivity having that direct insight. If you're stepping in maybe once an hour for 10 minutes, you might want to be in a container near the site, right? So you can walk over to the machine, you can do that work for 10 minutes really easily. So as you get that mean time to resolution down, the amount of manual work that operator has to do down, you start to get the ability to get farther and farther away, right? And that's also increasing safety, reducing commute times. Some of those are the values of this location-based part of the graph. But then when you start putting these two things together, right, you've got high productivity through high levels of autonomy, you've got the ability to be really far away from the machines that you're operating. That's where you start to get this scale factor, right? Because that one operator can now drive 10 machines across a handful of different sites, and that's really where we want to go. But we see the way that we get there is by kind of letting you choose that adventure, right? Starting in the cab, and as you get comfortable, being able to kind of migrate across to those different environments. And so for us, this Copilot system is what really kind of allows you to get on that journey and kind of very easily set and manage tasks, but it also helps us as a company, right? It lets us get into the hardest jobs, places where you would never think to put autonomy, right? Super dense urban projects where you get value from people detection, you get value from real-time 3D scanning, you get value from georeferencing, and that's data that now we can work to make our system better autonomously in those complex environments. I want to talk a little bit about the value of Copilot kind of from my own background. So, I have a little bit of a different sense of Copilot because when I was a kid, I was a Copilot. I grew up not very far from here, a little bit far in the grand scheme of things, about 3 hours west of Reno, which you've correctly identified as the middle of nowhere. And I spent many, many, many days of my childhood sitting on a toolbox next to my dad, keeping him company as he drove a disc or he drove a dozer or he drove a backhoe. And not only are these some of the best memories of my life, but they're also time where I was keeping my dad company, right? It's an incredibly boring job. It's good my brother's not here because I'll embarrass him by saying I have a vivid memory of my brother crying himself to sleep because the dust from the disc had blocked the sensor on his Walkman, and he couldn't listen to music while driving that disc every hour of the day, right? Just totally brutal, right? But by being little enough to fit next to the seat, I could sit there and I could keep my dad company. And he would let me be the co-pilot, right? He would let me take over for the long straightaways, and I could take control and I could operate that machine. But also, there were situations where, we'd have a brush fire and he'd have to drive the D8 into, a 20-foot flame to try to keep our ranch safe. And in those situations, he'd take me out of the machine and I'd be able to watch from a safe distance, right? And so those are the situations when I think about co-pilot, I think about that's what I want to give to operators, right? I want to get them out of the cab in those situations. I want to get them in a container with their coworkers or their friends that they can sit and talk, not be isolated in a cab, right? You got a tablet, you can handle manage a handful of machines while chatting with your colleagues, whether you like them or not, right? The other part of this experience was also recognizing how, sometimes when you see this kind of tech, people will start being a little bit afraid of like, oh, is this going to change the way that the whole industry works? What's this going to do for my job? And I will also say, as the person that was not only a co-pilot, I was also the one who solved edge cases, right? So I was the one who got out to kick out the hay bale that was in the way or to pick up the many, many rocks that would wreak havoc on our machines, right? And this kind of stuff, right? The hacksawing of the septic line to glue it back together when you strike it with that bucket, that's still going to be done manually, unfortunately. Humanoids are not getting there yet. So, even things like greasing the machine, refueling the machine, it's going to be decades before that work is done fully autonomously, right? So there's a lot of continuing roles that persist, hopefully not just the monotonous ones, but also those highly precise ones, the things where you need to jump in and do something because it's highly dexterous, it's highly communicated. The other part of this, right, is the communication between people, right? It's not just one person driving a machine. It's the benchman, it's the surveyor, it's the other trades, right? You hit somebody on the ground, as an operator, sometimes you can't decide what needs to happen. You've got to talk to other people. And that's something that robots, not very good at doing quite yet. You might have guessed part of the reason that I spent my PhD trying to get robots to pick up rocks is because this was not the most fun part of my childhood. So, if we talk through this system, right, I highly recommend you come see it in person, right? Seeing's believing in this industry. But what you see with this one kit, the Gravis Rack, is a handful of things, right? So we're doing autonomous excavation. We're giving you that machine guidance for placement. We're giving you real-time surveys and analytics, understanding what earth you've moved, what needs to be moved. We're giving that augmented reality to prevent utility strikes. We're giving that human form recognition to make your crews safer. And with the same system, we're able to offer you remote control. And the values we see here are multifold, right? So it's that safety aspect, less exposure, right? More awareness of those operators, more awareness of that autonomous system. It's that productivity, having consistent full buckets, high cycle times, being able to increase the throughput of your machines. It's the efficiency as well, right? You know where you need to dig. You know the depth that you need to hit. You're not going to overdig. You're not going to have that 5% plus rework that makes you have to haul that material out and back again. You've got predictability, knowing exactly when that work's going to be done. Cycle times are consistent. It's just like a metronome. When that thing does it, you're going to know how long that job's going to take. And at the same time, we see the really big value here in the transformation. More than 40% of the workforce is going to retire in like the next 5 years. How do we get the next generation interested in using these machines and being on site? Right? And our system is just like playing with an iPad, right? So if you can do that, you can drive an excavator. We've actually got a demo going where we will let anyone come out and start a thing, even if you are a kid. So speaking of the demos here, I want to give a little shout out to Devlon. So we've got our system here on their machine doing a demo that's interacting together with their dozer and with their loader, right? So it's actually bringing material to the machine, it's perceiving that material, it's doing bulk excavation, where actually as that material comes, it's understanding where it needs to dig. We've got demo times 5 times a day. We've also got demos in the festival grounds at Hitachi's booth. So here you'll see a really great preview of what it's like to have the system running inside the cabin. And you'll also see what it's like to step out the machine and let anyone from the public, it might be you, press play to actually have that machine go and dig a trench super efficiently, right, with very, very high accuracy. We've also got our own booth. It's not very far from here. It's like the closest booth ever. You just go out the door right across the way. You'll get to see Slate. You'll get to see our system up close, talk to our people, get to understand how we can help your job be better, increase your productivity, and get you on the pathway to autonomy. Thank you very much for the time you've taken to hear me out here. I hope that you spend some time with our team. I hope you spend some time looking into our technology. I'll give a little pitch, 2 things. 1, we're a finalist for the Next Level Awards, so please, if you go by our booth, scan that QR code, give us a vote. The other thing is we're looking to expand our team here in the US, right? So a lot of our projects have been in Europe and South America. We're starting to bring these systems into the US. If you're heavily interested in changing this industry, you've got experience in machine control, you want to work in sales, you want to work in service, please reach out to us. We're very, very happy to have that conversation and understand how we might fit into your future. Thank you all. Cheers.